In this video, I will describe my research study investigating the effects of surface temperature on climate disaster frequencies, and whether frequencies of climate disasters can be estimated from surface temperature changes. Climate disasters such as floods, fires, droughts, storms, and others have led to the destruction of homes and loss of lives, mostly due to the inability to prepare for the aftermath of these disasters. A model to predict surface temperature change by MJ Best presents a predictive model for surface temperature changes. By being able to estimate the frequencies of disasters based on the surface temperature change in a given year, it may help prepare for future disaster predicted. The problem addressed was to identify the correlation between surface temperature change and frequencies of various climate disasters. Throughout this research, some articles were reviewed to aid in the direction of the research. The first article being The Global Increase in Climate-Related Disasters by Vinod Thomas and Ramon Lopez, which explored the relationship between the surface temperature change and hydrometeorological or climatological disasters, focusing on tsunamis, floods, and so on in coastal regions. However, the research primarily focused on sub-factors without identifying a direct relationship between both variables. The second article reviewed was The Impact of Climate Change on the Risk of Natural Disasters by Martin K. Van Alsten, which investigated climate change's role in various disasters, including greenhouse gases. It acknowledged surface temperature as an influence, but did not directly examine the relationship between surface temperature change and climate disaster frequency. The final article reviewed was The Atlantic Forcing of Persistent Drought in West Africa by T.M. Chanal and others, which was one of the few articles that focuses research in Africa. It examined the impacts of the sea surface temperature change on drought frequencies, length and intensity in West Africa, providing an insight into the relationship between the surface temperature change and drought as a climate disaster. Our research question focused on if the annual change in surface temperature could be used to estimate the frequency of climate disasters occurring in a given year. The three associations we used to test was the correlation between the annual surface temperature change and climate disaster frequency, the annual surface temperature change and flood frequency, and the annual surface temperature change and storm frequency. The dataset was provided by the IMF Climate Indicator Dashboard. A sample included the data provided from nations in the Gulf of Guinea, including Angola, Benin, Cameroon, Democratic Republic of Congo, Republic of Congo, Equatorial Guinea, Gabon, Ghana, Liberia, Nigeria, Sao Tome and Principe, and Togo. However, Cote d'Ivoire, Guinea, Guinea-Bissau, and Sierra Leone were not included in the study because the data indicator didn't provide enough conclusive data to use for this research on these four countries. The measures for the two variables used was percentage change for surface temperature change and units of occurrence for climate disasters. The Pearson test was conducted on the three hypothesis claims to determine if there was a linear relationship between both variables in each claims. The bivariate graph suggested a strong linear relation between the two variables. However, when we tested our hypothesis claims, over the span of 42 years, there was strong evidence of a strong positive linear relationship between the annual surface temperature change and the annual climate disaster frequency. The statistical evidence further suggested that the annual surface temperature change accounted for 46% of the variation in the annual climate disaster. Another factor that could affect this could be the exact country when the disaster was occurring in. However, according to the data, the Gulf of Guinea basin could expect about 8.382 climate disasters for every increase in surface temperature change in a given year. For our second test, the bivariate graph showed a weak linear relationship between the surface temperature change and the storm frequency. Testing our hypothesis claims, over the span of 42 years, there appeared to be a strong evidence of a weak positive linear relationship between the annual surface temperature change and the annual storm occurrence frequency. The statistical evidence further suggested that the annual surface temperature change accounted for about 13% of the total variation of the annual storm occurrence frequency. A factor of this may be the location of the countries observed. Some may experience more and some experience less storm frequencies on average, depending on how close their borders are to the Sahara. The Gulf of Guinea basin, therefore, based on this data, can experience a count of 0.5552 storm count for every increase in surface temperature by 1 unit. For the final test, the bivariate graph showed a very strong linear relationship between the flood frequency and the surface temperature change. When we tested our claims, over the span of 42 years, there was strong evidence of a strong positive linear relationship between the annual surface temperature change and the annual flood disaster frequency. The statistical evidence further suggested that the annual surface temperature change accounted for about 51% of the variation in the annual flood disaster frequency. However, other factors that could affect this could be the exact country in which the flood occurred. The Gulf of Guinea basin can therefore experience about 8.3 flood disasters for every increase in surface temperature change by a unit of 1 a year. From our test, we notice a significant correlation between the surface temperature change and the climate disaster frequencies in the Gulf of Guinea. However, the relationship varied depending on the climate disasters that are being observed. Based on this, we can speculate that it may be possible to estimate how many specific climate disasters occur in a year depending on the surface temperature change of the year. And if compiled with surface temperature prediction models, could be used to predict the number of disasters that could occur within any given year and help governments and organizations prepare for those disasters. The research has some steady limits. The data provided by the IMF Climate Indicator did not include data for all Gulf of Guinea countries, and the countries that were provided, some had incomplete data. Also, our findings could only be significant to the Gulf of Guinea and may not also be the same as other countries of study. For future suggestions, I would suggest exploring alternative data sources for a more comprehensive analysis. Also, developing specific estimation models for each climate disaster depending on their relation with the surface temperature change. And finally, investigating the feasibility of integrating future surface temperature change prediction models with climate frequency estimations.